the last lecture we have seen about time scales and length scales of turbulent flow. We estimated that for flow through a pipe at a Reynolds number of 10 to the power 5, that is 1 lakh, we estimated the size of eddies and the lifetime of eddies, which is of the order of fractions of millimeter and a few milliseconds is the time fluctuations associated with these eddies. We also made the point that the eddies of different sizes are there. We have very largest eddies which are created by instabilities in regions of high shear, and through the action of hydrodynamic forces as a result of fluid motion, these eddies get broken up into smaller and smaller eddies, and the smallest size that can be sustained is the Kolmogorov eddy size, which we said was of the order of 0.0102 millimeters. And the question was that what could we do when we are given this nature of these turbulent fluctuations, where we have very small eddies compared to the typical length dimension of the flow or length dimension of the computational domain, and even length dimension of the grid spacing that we have. Given that these fluctuations are much smaller than this length dimensions, given that the time variations of the order of milliseconds is much less than the typical time variations that we would be interested in terms of the system behavior or equipment behavior, is it necessary for us to tackle these fluctuations? Okay. The other aspect of this is that these turbulent fluctuations render an essentially flow through a pipe to be fully 3-dimensional. If you were to take cylindrical coordinate system for a circular pipe, fully developed flow through a pipe is 1D, but this will make it, these fluctuations will make it 3D. Similarly, steady flow through a pipe is time independent, but these fluctuations will make it time dependent. So that means that no matter whether the flow is 1D or steady or 2D, we have to solve all the time the 3-dimensional unsteady form of the equations with very, very fine grid, and so that makes it we should wonder whether it is necessary to take into account all these fluctuations, what we call as resolve these fluctuations. That is, do we want our solution to show these kind of variations that are associated with turbulent flow, or is it possible to just smoothen these fluctuations, which is also what we do in many CFD computations. When we have oscillations, when we have oscillatory solution, we try to dampen those oscillatory solutions with smoothing terms. So is it possible to just smooth out these fluctuations and get a smooth solution? So this is where the concept of time averaging of fluctuations has come about. Here we have a typical time variation that is shown in the top figure, top right hand figure, where you see that over a time unit from 0 to 1 there are quite rapid fluctuations. A part of that is shown in the bottom figure, in which the same time unit is varying between 0.4 and 0.5, and when you expand the time scale like this, then you can see a variation which again looks quite a bit chaotic, but now you can see the individual points, how it is changing from time to time at every time step. So if you take an interval, for example, if you take the time variation between 0.42 and 0.48, which is what we have taken here. So we can introduce the concept of time averaging, where if f is a parameter, it is a flow parameter like the velocity component in one direction, in any direction, then we can say that it is fluctuating about a mean quantity, and the mean quantity is given here as indicated by the over bar, that is f over bar, and at the velocity value, the parameter value f at any time is decomposed into a mean component and a fluctuating component, which is indicated with a prime. So that is f is equal to f bar plus f prime, where f bar, that is the time average quantity, is time average of ft dt over a time interval which is capital T. So that is what is shown here, and with respect to the, with reference to the figure at the bottom, where you see the time variation between 0.4 and 0.5, if you take the time interval capital T to be 0.06 as shown in the figure, then the average value at 0.45 is integral of f dt between 0.42 and 0.48 divided by the time duration 0.006, and that will give you the horizontal line that which indicates the average value at over that interval. Okay. So this is the average value over this time interval. Now if you take this particular time instant, then we can say that the red one is the actual value u of t at that particular time instant, and this is decomposed into the mean value, which is this dotted line all the way up here, and the fluctuating component is this part. So the mean is this whole thing plus the fluctuating component, which happens to be minus at this point, so that the actual value is less than the mean value here. If you go to some other time, for example here, then you have a mean value plus a fluctuating value which is positive. Again here a fluctuating value is what is above this, and the mean value is what is below this. So over a particular time period capital T, the value, the fluctuating component is both positive and negative. Within the time period where we are averaging, the time average value is constant. Okay. So the time average value is such that if you integrate the fluctuating component over the time interval, then it becomes 0. Okay. So this is how we define the time averaging of any particular parameter f. In fluid flow we have several parameters. We have u component, v component, w component, we have pressure. All these things are simultaneously varying, temperatures varying, concentration, all these things. So this time averaging operator is such that if you take the time average of the addition of two parameters f plus g, so the time average of f plus g is just the sum of the time average quantities. So that is what is shown in the first relation here. Time average of f plus g over bar is equal to f bar plus g bar. Similarly, time average of a derivative, that is dou f by dou x I time average, is the derivative of the time average quantity. So that is dou by dou xi of f bar, which is the next relation. And the relation after that says that even if you are looking at time derivative of f, that is dou f by dou t, and then you take time average of that, then that is dou by dou t of f bar. Okay. So even time average of a time derivative is the time derivative of the average quantity, but there is a difference between the left hand side and right hand side of this particular thing here. Okay. On the left hand side, when we talk about dou f by dou t, that is variations over very small times of the order of milliseconds and even microseconds. On the right hand side, when you talk about time average of the time derivative of the average quantity, you are talking about time steps, time intervals, delta t's, which are much larger than the capital T that you have used for time averaging. Okay. Given that the turbulent fluctuations in turbulent flow are very rapid and highly localized, to such an extent that these are much smaller than the typical length scales and time scales of actual flow variations. For example, length of the computational domain or the time scale of simulation that we may want to do, like 1 hour or 10 minutes or like that. That these can even be smaller than the grid spacing that we typically employ and the delta t's that we usually use for simulations. Given all these things, is it possible to smooth over these fluctuations by doing some kind of averaging? This is the idea behind time averaging of fluctuations, where if you take a parameter f, which can be the velocity, the instantaneous velocity component in a particular direction, pressure or temperature, concentration of a species, any parameter can be decomposed into a sum of a time average value f bar plus a fluctuating value f prime, where the time average value is evaluated as integral of f dt over a time period which is capital T by 2 before and capital T by 2 after. You take this example here, this is actual time variation. Within that we are focusing over a smaller window between 0.4 and 0.5 here, and since we have expanded the window, we can see a more the variation more clearly here. It is like this, and if we choose capital T, the time period over which we are averaging, to be 0.06, so that at 0.45 we want to know what is the time average value. We integrate it between 0.42 and 0.48, and then we say that the average value over this time interval is this value here. Now within this interval, the value of f is changing, and specifically at this time the true value is what is shown in the red one, and this value is decomposed into a time average value, which is this whole thing, plus the fluctuating value which is given by the dotted line here, and in this particular case the fluctuating value is negative, so that the time average value minus this value has given us this one here. If you take some other instant, maybe at this particular instant here, now you have the instantaneous value is greater than the mean value, so that means here u plus f plus is positive. So over this time interval, f plus f prime is both positive and negative to such an in such a way that the average value of f prime over this time interval is 0, and average value of f over this time interval is f bar. So at any time instant, f is decomposed into f bar plus f prime. In a case where f bar is constant with time, for example, you take this thing, if you take the average here, then it's almost looks like it's constant. Then if f bar is constant for every parameter, then you can say that it's a steady turbulent flow, in which a time average quantities are steady, means that you have a steady turbulent flow. So even though within this time period over which we are integrating, f is constantly changing, you can still claim it to be a steady turbulent flow. So this f is therefore some integrating function. Okay, so the f bar, the time averaging, is an integrating operator here. Now if you when we write our equations, we are always writing in terms of this plus this term plus this term and like that, and in a particular term you can have different parameters. Here we are taking two parameters here, and if you take the time average of sum of f and g, where each of f and g is a different parameter, then you can plug this into this and you can show that the time average of f plus g is just the time sum of the time average quantities f bar and g bar, and the time average of a space derivative, that is time average of dou f by dou xi, is equal to dou by dou xi of the time average quantity. So that is dou by dou xi of f bar. This applies even to the time derivative. You can say that time average of dou f by dou t is equal to dou by dou t of f bar. The difference between the left hand side and the right hand side here is that in the left hand side this dou f by dou t can be where this delta t here can be of the order of milliseconds, and here this delta t that we are talking about to describe the time variation of the time average quantity, this delta t must be much larger than the slowest of turbulent fluctuations. In the case of pipe flow, the slowest fluctuation was associated with the largest eddy, and that was of the order of 80 milliseconds. So, this delta t that appears on the right hand side here must be much bigger than 0.08 seconds. So, maybe the order of 10 seconds. 10 seconds is still quite a lot, quite small in terms of the typical time variation of a system or an equipment that we are interested in. If you are looking at startup of a chemical reactor or a plant, then that may take hours, and to get a value every 10 seconds is still pretty good resolution, time resolution of how the system parameters are changing over this hours or over this days during which the startup takes place. Okay. So, this particular approximation, that as a result of time averaging we are no longer allowed to talk about changes over milliseconds, but maybe changes over seconds and tenths of seconds, is not too severe an approximation, and we can make this kind of thing. Now, an interesting thing happens if you take the product of two quantities and time average it. So, the time average of a product Fg, like product of uv that appears dou by of uv, is a term which appears in the momentum equations, and f is u and g is v. So, if you write down the time average of this product, then you can show that it is the product of the time averages that is equal to f bar plus g bar plus the time average of the fluctuating components f prime and g prime. Okay. So, this f prime and g prime are that time average quantity is not necessarily 0, and they are 0 only if f and g are statistically independent. For example, if you say that f is the temperature of the day at a particular shop and g is the number of ice creams sold at that particular shop, then every day there is going to be variation in terms of temperature of the day, the peak temperature of the day, and then every day there is going to be variation in terms of the number of ice creams that have been sold in that particular shop on that particular day. Okay. But if temperature is high on a particular day, then more people prefer ice creams. So, f bar is the variation from the mean value of the temperature on a particular day. On a particular day it may be hot day, so that means f prime is positive, and g prime is the number of ice creams sold, the variation on that particular day compared to the mean value. Since on a hot day more people prefer ice creams, on that particular day you will see more ice creams sold, so g prime is going to be positive. So, that means that on the average you can expect the time average of f prime g prime, the time average is indicated by these greater than and less than symbols here, this will be positive. Now, if you look at the same shop and then if it is also selling coffees, and since on a hot day fewer people prefer hot coffees over ice creams, then you can say that on a hot day the coffees sold, that number will dip. So, that means that h prime, which is the variation of number of coffees over the mean, on a hot day f prime is positive and h prime is negative. So, on a time average basis you can say that f prime h prime will be negative. So, these f prime g prime bars are not necessarily 0, and they depend on what kind of process we are looking at. So, we cannot straight away say that at the time of time averaging this f prime g prime bar here can be reduced to 0. Okay. So, this cannot be made 0. It can be 0 only if we know that f and g are statistically independent they are statistically independently varying. Okay. So, otherwise we have to retain this. Using this operators of time averaging, we can time average our governing equations, so that we can eliminate the influence of these rapid fluctuations from that. So, if you take the continuity equation, you have in 3D incompressible flow, you have dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. Now, that is the equation, and we can do any mathematical operation on that, and we should be okay with that. So, we do the integration as given here, and then so effectively we are doing time averaging of both sides of the equation, and so you get time average of the LHS is equal to time average of the RHS, and this will not change the equation, the validity of this conservation equation. Now, if you now look at this, there are 3 terms, it is sum of 3 terms. We can apply this rule here, and we can write this as time average of the individual derivatives. So, time average of dou u by dou x plus time average of dou u by dou y plus time average of dou w by dou z equal to 0. Now, we look at this, and then we can apply the derivative rule here, and then we can write this as dou by dou x of time average u here, dou by dou y of time average v, and dou by dou z of time average z equal to 0. So, by doing this time averaging, we have converted this instantaneous equation, the mass conservation equation, in which the instantaneous values UVW are appearing. From that into, we have converted into mass conservation equation, in which only the time average values are coming. And what is the gain that we have made? Time average quantities will change much more slowly. So, that means that you can have much bigger time steps than what is needed if you want to solve the original equation. And that is the idea, that is the advantage that we wish to gain through time averaging, average out these fluctuations. Now, if you do the same thing for the momentum equation, slightly more difficult here, but the same idea will be there. So, you have consider the x moment balance equation in 3D. So, you have dou u by dou t for incompressible constant properties. So, you have dou u by dou t plus dou by dou x of u square plus dou by dou y of uv plus dou by dou z of uw equal to minus 1 by rho, rho is constant incompressible flow, dou p by dou x plus nu, the kinematic viscosity, which is constant, dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. We can neglect the influence of gravity here. So, we time average both sides. So, time average of the LHS equal to time average of the RHS, and since this is sum of these terms, we can write this as individual terms, time average of dou u by dou t plus time average of dou by dou x of u square, time average of dou by dou y of uv, like that, and similarly time average of the pressure gradient term, time average of the individual viscosity terms here, like this, and we can apply the corresponding rules that we had earlier for the derivatives, time average of derivatives. So, we can write this as time average of u bar, and here we have time average of u square, and you have dou by dou y of time average of uv, dou by dou z of time average of uw, and here you have rho is anyway constant. So, dou by dou x of p bar, and here say 2 derivatives are there. So, they come out of the time averaging. So, you can say dou square by dou x square of u bar, dou square by dou y square of u bar, dou square by dou z square of u bar. Now, on the left hand side here we see dou by dou x of u square. So, that is a product u times u, and here you have dou by dou y of uv, that is again product of uv, and we know that time average of Fg is the product of the time average quantities plus the time average of the fluctuating quantities. So, we can write this as dou by dou t of u bar here plus dou by dou x of u bar square plus u prime square bar. So, this is the time average of the fluctuating component, the product of the fluctuating component. Because g and f are the same, u here you get u prime square, and this term here becomes dou by dou y of u bar v bar plus time average of u prime v prime bar, and here again you have dou by dou z of u bar w bar plus time average of u prime v w prime. So, we have this equation here. We can write similarly the y momentum and z momentum equations, and they become dou by dou t of v bar plus dou by dou x of u bar v bar plus u prime v prime bar, and dou by dou y of v bar square plus v prime square bar, and we have already mentioned that this is not necessarily 0 and this is not necessarily 0. That depends on whether u and v fluctuate independently or there is some correlation between them. Okay. So, like this, and you have the z momentum equation is dou by dou t of w bar plus dou by dou x of u bar w bar, like this. Now, if you look at these equations, what we would like to have are the equations, momentum equations, conservation equations expressed in terms of time average quantities, so that we can make use of large delta t and large delta x, and we do not need to have a very fine grid and very fine time step. And when you look at that, we can see that that is being satisfied by these conservation equations, because every term has a derivative and that derivative is talking only about time average quantities. So, from that point of view, we have succeeded in representing the momentum and continuity equations, mass conservation equations in terms of time average quantities. But we have a problem, and the problem is that we can write the overall equations for all of them using Einstein's summation of repeated index convention. That is, in this term you have m is a subscript which is an index which is being repeated here because it appears twice in this term. So, then that means that this implies sum over the 3 quantities, m equal to 1, m equal to 2, m equal to 3, and that gives us dou u1 by dou x1 plus dou u2 by dou x2 plus dou u3 by dou x3, and that becomes the time average the continuity equation. And similarly, the time average momentum equation is like this. Okay. Now, what do we see here? We see that you have the time average velocities here and you have time average velocities appearing here, but here is a new term u prime bar ui prime bar and ui prime times u m prime over bar. Okay. And this is the average time average pressure and this time average velocity. So, this term and this term, these terms and these terms are not new, those are the ones that we wanted, but in the process we also got these extra terms, and these terms are 0 only if the u and v are independently changing, and we know that u prime bar is not 0, it is 0 because u prime is positive and u prime is negative, but when you take u prime bar times u prime, then that is always positive. So, the only way that u prime bar is 0 is when u prime is 0 completely all the time, that is when you do not have turbulent fluctuations, when you have laminar flow. But if you have turbulent flow, then u prime square bar is not 0, and similarly v prime square bar is not 0, and these terms are appearing in the momentum equations. So, that means that you have a problem as a result of fluctuations, as a result of time averaging. You are introducing 6 additional variables, that is u prime square bar, v prime square bar, w prime square bar, u prime v prime bar, u prime w prime bar and v prime w prime bar, and actually measurements show that these are not 0. For example, this is a typical variation of u prime square bar and v prime square bar, w prime square bar and u prime v prime bar in pipe flow, and these are varying, we will see more about this with respect to space, and so these are not 0. So, if these are not 0 and these are remaining in the equations, so that means that this set of 4 equations, that is 1 continuity equation, 3 momentum equations, we have 4 equations and they feature 10 variables. You have the 3 velocity components, that is u bar, v bar, w bar. We have p bar, the pressure, the time average pressure, and in addition to that you have these 6 components, 6 terms which are known as Reynolds stresses. We will see why this is called Reynolds stresses, and these are also non-zero. So that means that you have 10 variables and you have only 4 equations, and so that means that as a result of time averaging you have introduced more number of variables, you have not got more number of equations. Okay, so you had the same 4 equations but involving time average quantities and 6 other time average quantities which are not zero and their variation is not known a priori, and simple measurements show that even for simple flows they vary in a complicated non-simple way. So this is what is known as the turbulence closure problem. When we want to do the time averaging of equations in order to smooth out these oscillations and represent the conservation equations in terms of time average parameters of the flow, then in the process in some of the equations we have extra terms, and these extra terms are such that these are not necessarily zero, and we do not know how they vary in the general case, because even in simple case of fully developed pipe flow, as you move away from the wall, which is given here as dimensionless distance from the wall here, that is why we put it as y plus, dimensionless normal distance from the wall, then each of these quantities is varying in a non-monotonic way. They are going up to a peak and then they are falling back like this, and each of them are reaching different values and slightly at different times, and this u prime v prime bar is also changing. And so the fact that these are exhibiting a complicated spatial variation and which is not known a priori means that these terms will remain as variables in the equations, and if these are variables in the equations, you have 10 variables and you have only 4 equations, so you cannot solve the problem. You do not have a closed problem, you have a problem of closure of the mathematical problem involving time average gauge equations, and we need to do something more about these equations. We need to bring in extra equations. So that will be the subject of the next lecture. So in the next lecture we will see what kind of closure models we can bring which will give us reasonable solutions for the turbulent flow.